Hello all, we are starting our next topic, resonance spectroscopy. Resonance spectroscopy is mainly classified into nuclear magnetic resonance spectroscopy and electron spin resonance spectroscopy. You may be familiar with the words NMR and ESR. These are a different kind of spectroscopy compared to others. Both these branches are essentially similar, being based on same principles. Here the matter interacts with magnetic field of light and not the electric field. The magnetic field is used to provide the energy level separation probed by the radiation. Both these spectroscopies involve spin. Spin is a fundamental property of an elementary particle. For example, an electron, which is an elementary particle, rotates on its own axis and has a spin. Thus the spin is manifested by the presence of an intrinsic angular momentum. And the magnitude of this spin angular momentum is, I am giving the modulus, and since I am not bothered about the sign, is equal to h by 2 pi root of s into s plus 1, where s is the spin quantum number. It is this rotation, according to quantum mechanics, it is quantized. For an electron being a charged particle, the spinning electron gives rise to a magnetic field whose axis coincides with the axis of spin, so they are equivalent to a minute magnet, and this magnetic moment will be associated with the spin as mu s. The magnetic moment of the electron will be proportional to this, that is spin angular momentum, and can be equated by this expression, where Gs is the electron G factor, E is the charge of electron, and m is the mass of electron. So the magnitude of nuclear magnetic moment can be represented as, here we can replace the vector with the quantity s into s plus 1. We will get the magnitude. And also we can have an equation. We are substituting these values as beta s, where beta s is called the Bohr magneton. The magnetic moment of electron related to the spin will be this equation. Further, from quantum mechanics, it is known that the energy of interaction of the magnetic moment with an external magnetic field applied along z direction will be E equal to minus mu s into bz, where we can substitute for mu z as we have generated the equation earlier, and we will get the short form of an equation as, where ms, here it is the two orientations of electron spin that are allowed in the magnetic field by quantum mechanics, that you know it is plus or minus half. And therefore the plus or minus half, that is the energy, the plus half and minus half, both levels can have an energy which is proportional to the applied magnetic field, and can have the expression. It should be noted that in the absence of magnetic field, there is this energy existing in the absence of this magnetic field, but both of the components have same energy, that is they are degenerate. But this degeneracy of the spin component is removed by the presence of magnetic field, which is known as Siemens splitting of energy levels. Splitting of spin components in presence of magnetic field is the Siemens splitting, and hence they are separated as one level towards upward and other level toward downward, and there will be an energy difference which will be represented as half minus half. Half minus half. It can be the difference. Minus half minus. It can have minus sign or plus sign. Here also I am representing only the modulus of energy difference, which is Gs, beta S and Bez. I hope you have got this energy difference. This by the difference between the two energy level E half and E minus half. Then, like electrons, proton and neutrons in nucleus are also elementals. It also possesses spin. For nuclear particles, there is a problem that the nuclear spin will be always the resultant spin of proton and neutron, as both have spin angular momentum, and it is denoted by spin angular momentum I in the case of neutron or nucleus, proton or nucleus. Spin angular momentum I will be the resultant, and it is given by the expression h by 2 pi root of I into I plus 1 by quantum mechanics, where I is the spin angular momentum for nucleus. In the case of hydrogen, protium, what is hydrogen or proton? Only one proton in nuclei, so the spin angular momentum for nucleus is, for one proton it will be half, I equal to half. But you consider the case of deuterium, where contains one proton and one neutron. This must have a resultant spin. The spins of proton and neutron, if they are aligned parallel, it have half plus half will be 1 will be the resultant spin, and if it is anti-parallel, I becomes 0, which is the resultant spin. Thus, the deuteron is expected to have spin 1 or 0, but it's found that in ground state, deuteron has a spin of 1. Thus, it is difficult to predict the resultant spin of nuclei having more number of protons and neutrons. So, some rules are designed which are helpful in predicting the nuclear spin. It is given in the table. That is, if for a nuclei or an atom, if the atomic number and mass number both are even, there will be no spin quantum number. The spin quantum number I will be 0. So, example, you know for 6 carbon 12, 8 oxygen 16, 16 sulfur 32 both have even atomic number and mass number. For them, the I will be 0, so that there will be no nuclear spin states or energy levels, or this cannot give a resonance spectroscopy. Next, if the mass number is odd, this is the only criterion. Atomic number can be odd or even. Mass number if is odd, then you know the examples: hydrogen, fluorine, phosphorus, boron, carbon 13, both of all have the spin I value will be the half integer. Here you can have 1 half, 3 by 2, 5 by 2, etc. Here hydrogen, fluorine, phosphorus, all of them have carbon 30 half spin. Boron have the spin value 3 by 2. But here no problem, you only have the spin, or you have to study only the proton or C13 spectrum, so that both of them have the I will be half. Okay, then for nuclei having mass number even, or atom having mass number even and atomic number odd, this deuterium, nitrogen, etc., they have integer value of spin 1, 2, 3, etc. Here for deuterium and nitrogen, this one can have 1, 2, 3, etc. for the different nuclei. This is a general rule regarding the prediction of nuclear spin, as it is difficult for us to find out the spin easily. Since the nucleus also possesses an electric charge, being a charged particle, it also has some magnetic moment, which is as electrons, mu n equal to Gn into QH by 4 pi mp. You can see the difference, that is Gn, it's the nuclear G factor, Q is the charge of proton, mp is the mass of proton. This is the only difference. And you can write this expression as, can have the value beta n for this constant, and it is known as a nuclear magneton. Here also there is interaction of magnetic moment and magnetic field, which is equal to minus mu n into Bz, and also can have, here also have energy levels, also have a Siemens splitting in presence of magnetic field, and they have energy difference of delta E, Gn, beta n, Bz. Now before we go into the details of these spectroscopic techniques, let us compare the two spins, nuclear and electronic, and the associated magnetic properties of the two spin particles, electron and proton. That is, here's the table. Here the difference for electron and proton, the spin is half, and the spin angular momentum associated with the spin for electron is modulus of S, and for nuclear proton it is I. Next, magnetic moment associated with the spin, which is, as you have already seen, it is mu s equal to minus GSB beta s in the root of s into s plus 1. Here mu n equal to, you can see there is a negative sign here and it's a positive sign. That is, here for proton, the nuclear magnetic moment and the charge of proton are in the same direction. So here there is no need of a negative sign, but this is showing that electron and the nuclear charge of electron and the magnetic moment are in opposite direction. So we are giving a negative sign. This is the only difference. And for electron, the Gs is accurately calculated to be 2.002. But for nucleus, Gn can be obtained from experiment, as it is different for different nuclei. Here, this is for proton, this value is 5.585. Now, the degenerate energy levels for electron spin and nuclear spin states are given by the energy equation, whereas Ms and Mi are the orientations of the spin, nuclear spin or electronic spin, plus or minus half. And in the presence of an external magnetic field, there will be Zeeman splitting, and the energy separation for electron spin states is delta E here, and it's delta E for nucleus is this. Now we can draw the schematics of the energy levels of electronic and nuclear spin states. First we can see the Zeeman levels of electron spin states. Here, when we are not applying any magnetic field, both the energy levels plus or minus half will be degenerate, both having the same energy, and we are applying the magnetic field, which is not equal to 0, means we are applying a magnetic field, the energy level separation. If you are increasing the magnetic field, the separation will increase. And similar here you can see a Zeeman split minus half, there is a plus half, and with having an energy difference. Now I think you get what is the splitting, the idea about what is the splitting. Similarly, you can see for proton spin states, similar splitting in by the applied magnetic field, and will be here for proton, since it is a proton, it is plus half will be the lower, and electron it is the minus half will be the lower. That's the difference, and plus half minus half, and there is also an energy gap which is Gn beta n Bz. So here you might have a think there will be a negative sign. So I have said already that it is only I am taking the modulus. Not I am concerned not about the sign. So if you see both the energy level separation by the applied magnetic field, the energy, we can separate the energy levels by the application of a magnetic field. In order to induce transition, or in order to let the spin flip from one upward direction to downward direction, or to different direction, we must apply an electromagnetic radiation. There is the importance of spectroscopy, which will be perpendicular to the direction of applied field. That is, if we are applying a magnetic field so that the spin degeneracy removed, and in order to induce a transition, we must apply an electromagnetic wave. The spin flips. The spin in the there is a transition from downward state to upward state, or the spin flips when the energy of the photon electromagnetic wave will be exactly equal to the energy gap, or the delta E, between the two levels. That is h nu. When h nu, the energy of photon or radiation will be equal to the delta E value, or the frequency of radiation when will be equal to the delta E by h, there will be a transition where delta E is this for nuclear spin states and this for electron spin state. That is, if this frequency matches with the frequency of photon in the case of electronic spin state, there is a transition, and here when the frequency becomes this, there is a transition. So since the frequencies match, this is the resonance condition, and that is why such a spectroscopy is known as resonance spectroscopy. For the transition between nuclear Zeeman levels, the spectroscopy is known as nuclear magnetic resonance spectroscopy, or NMR. And for transition between electronic Zeeman levels, it is known as electron spin resonance spectroscopy, or ESR spectroscopy. That I have said that both of these spectroscopy based on same principle. You have to note one point that the Bohr magnetone beta S is about of electron, or magnetron of electron, which is the Bohr magnetone, is about 2000 times greater than nuclear magnetone. Since from the equation in the previous slide, you can see they are inversely proportional to mass. And you know the mass of nucleus is always higher than mass of electron. So that the frequency of NMR is much less than the frequency of ESR. So the ESR frequency falls in the microwave region, whereas the NMR frequency in the less frequency radio wave region. That is, ESR spectrum will be observed in the microwave region and the NMR spectrum will be observed in the radio wave region. Here we will end this lecture, and in the coming lectures we will deal with the details of NMR and ESR. Thank you very much.